The idea that light behaves as both a particle and a wave seemed crazy at first, when early in the 20th century the evidence defied any other explanation. Eventually, physicists were compelled to accept that the world is just strange in that way, and there are other features of light that have defied common sense, yet compelled acceptance. This is a presentation, an illumination of the nature of light that will seem crazy at first, but it actually provides a coherent explanation of its strange attributes. It might have been established long ago if not for Hermann Minkowski. He led a diversion. He was a professor, primarily a mathematician, actually. Einstein was his pupil, and the young Einstein hated mathematics. Minkowski called Einstein a lazy dog, and he was probably instrumental in preventing Einstein from obtaining an academic position in physics. Einstein had to take his doctorate and go to work as a patent clerk. Minkowski, based on the exotic mathematics that fascinated him, believed the geometry of space-time to be parabolic, not linear, not straight, not flat. And so when he realized that this upstart Einstein was onto something with relativity, he developed the Minkowski diagram seen here to give the theory a geometric expression. Not surprisingly, his diagram treats the geometry of relativity as being parabolic, and he made a simple, pre-relativistic error in its construction. He projected the observer's clock speed onto light, a fundamental violation of the theory of relativity, which holds that every physical body has its own clock, and its clock will move relatively slowly the more relatively rapid it moves in space. Look at the motion of light in Minkowski's diagram. It moves on a diagonal relative to an observer, meaning that light is represented as moving 1 light second per second relative to the observer, who is stationary in space and moving 1 second in time, although the clock speed of light, according to relativity, is always 0. Minkowski's diagram has been a standard in relativity since 1908, and it is a scandal to theoretical physics that it has been accepted without question all this time. This alternative diagram, which my mother called the Arnold diagram, projects light according to physics, not according to a mathematician's imagination. Relativity revealed that the clock speed of light is 0, and so it should move directly along the space axis with a clock speed of 0. And this is crucial to a clear understanding of relativity, and crucial to an understanding of the nature of light. Two of the most perplexing features of light are clarified by a truly relativistic diagram. Why light speed is the absolute maximum speed, and why no matter how fast you might go to try to catch a light ray, it will continue to go that much faster than you. This diagram correctly shows a vector representing the space-time motion of an observer called A at rest, not moving in space, and therefore moving perpendicular to space in time. According to relativity, a body in relative motion, like body B here, going 80% the speed of light, has a clock speed, a relative motion in time, 60% that of the observer A. B's vector, called its world line in space-time, completes a perfect 3-4-5 Euclidean triangle. It forms the hypotenuse of the triangle, and it is necessarily equal in length to that of the observer, whose observations constitute the square sides of the triangle, and so stands in the same relationship as a hypotenuse. This reveals an important physical principle, no thanks to Minkowski. The world line of every body, whether at rest or in motion, relative to an observer, is the same length as that of the observer. This principle of equality of world lines indicates that the world line of light, shown here as vector C, moving directly along the space axis with 0 clock speed, is moving at the absolute maximum speed possible, because anything that has clock speed has a world line of the same length, but it moves partly in time and therefore less in space. And the diagram indicates that an observer moves as far in time as light does in space. So 1 second in time is equal to the same distance in space, 300,000 kilometers. Incidentally, light speed isn't, as it's often claimed, a constant in a vacuum. Imagine yourself in a geostatic orbit above the Earth, looking down on a colleague on the surface who is busy measuring the speed of light. As is often recognized, and the GPS system depends upon it, her clock speed is slower than yours because she is deeper in the gravitational field. And so the speed of light at the surface must be slower than at your elevation. So light speed is a conditional constant. It is constant at any elevation at a gravitational field, but it is slower from below, and it is faster from above. But I digress. With this diagram, some of the strangest features of relativity can be appreciated. I'll only touch on the pertinent aspects here, but a detailed treatment can be found at the link on Relativity listed below the screen. Note that observer B in uniform motion relative to A has a different orientation to space than A. Both can be considered at rest, so both are moving perpendicular to space in their own coordinate system. And so, while A observes B's clock to be moving slowly, B is in the same circumstance, observing that it is A's clock that is moving slowly. This can be clearly seen if the diagram is rotated so that B's world line is vertical. The observations of both observers mirror each other. Even their measures of distance are relative and mirrored. With geometric clarity, instead of the usual tortuous mathematics on a whiteboard, it is evident that there is nothing irrational or nonsensical about these features of light. Lots of champions of a return to classical physics can relieve themselves if they can just appreciate these basic relativistic relationships. There's a lot going on in this diagram. What's important here is just to show how two observers in relative motion and at the same elevation will agree on the speed of light. Points PA and PB are actually the same physical object. A signpost that becomes illuminated sometime after A has flashed a beam of light toward it, just as B is flown by A in the same direction as the light. A observes the light as hitting the signpost after 5 seconds at a distance of 5 light seconds, while B observes it to go only 3 light seconds in 3 seconds. Thus, despite the relative motion, despite the length contraction, they agree on the speed of light. There are more puzzling features of light than can be clarified with a space-time diagram, but their resolution requires a long leap toward an openness of mind to what may be the strangest idea you have ever been asked to indulge. So here it comes. It is axiomatic in relativity theory that unaccelerated motion among material bodies is relative and limited to less than the speed of light, while the motion of light is invariant and an absolute limit. We've just seen it geometrically. It is consistent with relativity that motion in time is an integral property of mass, and the clock of a material or massive body will not stop entirely no matter its relative velocity. In contrast, light is massless, and its clock, if it could be said to have one, is invariably motionless. It may follow that light is actually absolutely not moving in time, and if light doesn't move in time, it may be meaningless to say that light moves at all. Well, this idea that light might be at absolute rest no doubt seems a very odd and unlikely suggestion at first impression, but I hope to justify it here by an appeal to the explanatory power by which it may be judged superior to the conventional interpretation. Leaving acceleration aside, considering just uniform motion, a space-time diagram shows, and the mathematics of relativity expresses, that to move in time is to move perpendicular to space. And because such movement in time would always be in space, it would be a simultaneous moving away from one point and toward another, perpendicular to all 3 dimensions at once, necessarily all 3, because a universe of massive objects moving in time perpendicular to only 1 or 2 dimensions in space would be incoherent and nothing like what we observe. So to move in time perpendicular to the 3 spatial dimensions would be to radiate or spiral away from one point. There is no other way to move perpendicular to 3 dimensions. It would be to move away from one point in space and simultaneously concentrate toward another, wave-like. A visualization might look something like the representation in this drawing. The blue circles represent the radiating wavefronts, the red circles the concentrations from point to point. As is thought to be true of light, the wavefront of a mass might propagate to any point on the next wavefront, but presumably, without an application of force, a spatial direction would continue along the same general trajectory, with maybe some degree of deviation at the quantum level. In order to ascribe to mass the wave-like behavior we normally attribute to light, it is necessary to posit the four-dimensional motion of mass as a trajectory that fluctuates in a cyclic manner along its wavefronts. For two observers standing side by side, radiating parallel in time, their wave-like motion would be undetectable to each other. If they are in relative motion, they will normally be radiating and concentrating with just a slightly different space-time orientation. The wave-like component of their motion will be so close to synchronous and parallel, it will still be unnoticeable. We naturally discount the wave-like motion of the things moving parallel with us in time and attribute them instead to waves of light, so the interactions with photons appear sometimes as particles, sometimes as waves, as a duality of particle-like and wave-like stuff. In some circumstances, as when light seems to be refracted, there can be a wave-like phenomenon, which, though commonly attributed to the wave-like nature of light, can be shown as due to a sort of reflection of the radiation of mass. But I'll reserve a discussion of that until considering the double slit effect further on. If the photon is regarded as a strictly spatial, atemporal object embedded in space, set in space, an observer who regards herself as at rest and light as being in motion, while the observer is actually moving across space in time, that observer will experience direct interactions with photons as impacts with moving particles, and experience indirect interactions as the manifestations of waves. The apparent motion of light would be the reflection of an observer's motion in time across space, and with this we would have a resolution of the wave-particle paradox, a problem that has long eluded satisfactory explanation. The wave-particle duality of light is what we commonly experience in our interactions with light, and it has seemed irreconcilable with common sense to be both a wave and a particle, or it did until science resigned to it being just the way it is. What I'm proposing is no more absurd than wave-particle duality, but of course a question or an objection immediately arises. How can it be said that light doesn't move when we commonly experience light to travel from a source and shine upon or reflect from the objects around us? The light from the sun seems obviously to travel millions of miles to shine upon the earth. Well, let's first acknowledge that we have brains that don't work well in trying to conceptualize four-dimensional interactions. In an ongoing situation, we can describe a light source as depositing a series of photons in space, while the source, the observers, and every mass in the room, including the atoms in the walls, are radiating and concentrating in time across space, all in parallel with one another, because each is at a relative state of rest. For each photon deposited, there will eventually be an intersection with a mass, an atom, depending on which of the spatial trajectories of the masses in the room are oriented toward a photon as its temporal wavefront crosses the photon's location. So consider this situation. 4 people are standing against each of the 4 walls of a room, and a light bulb is shining from the center. Every massive thing, the light bulb, the people, and the walls, are radiating parallel in time, perpendicular to space, as the bulb in effect deposits a photon in space. Light is normally thought of as radiating across space and as potentially intersecting with the massive body at any point along its circumference, but we are considering the opposite relationship. In order for bodies moving in time to have a direction in space, there must be some sort of spiraling component to motion in time across space, with those not in relative motion sharing the same direction, with each revolution along the wavefront constituting a wavelength, so that any person and any atom in the walls might be the first to concentrate upon the location of the photon and absorb or reflect it. And to reflect it would be to redeposit it. Those others moving in time would either pass its location while concentrated elsewhere along their wavefront, or would have yet to cross its distance from the moment it was deposited. Thus does Mr. Brown see the light. Wave meets particle, and there is no duality. Of course, it may be denied that this is what happens, that light is just a strange wave particle after all. But the simple example provided here can yield explanations for what have been the most inexplicable, seemingly impossible, dual properties of light. If light is considered to be at absolute rest, if the apparent motion of light is actually the reflection of the motion of mass in time, however absurd the idea may seem at first, the question is, what other paradoxes could be resolved? What phenomena can the hypothesis explain that cannot be explained otherwise? There are two classic experiments that have been carefully studied and finally reconciled to a hopeless non-explanation, but which can be explained if light is regarded as being at absolute rest. A phenomenon now taken to be just a strange feature of reality is the oddity of the relationship between light and mass brought to light, pardon the pun, by means of Young's classic double-slit experiment, in which slits or pinholes in the screen produce seemingly inexplicable manifestations of particles of light acting wave-like. Photons have been found to behave differently when passing through a slit in a screen, depending on whether there is another slit some distance away, and it seems to defy a conventional explanation. When only one slit is open, the pattern is as expected of particles. There's a single region of hits of photons against the screen, with a concentration toward the center of the pattern. When a second slit is opened, there is an interference pattern indicating the light has become wave-like. Young's experiment is depicted here in the conventional manner, treating light as moving and mass as at rest. Point P represents a light source. A1 and A2 are slits in screen S1, and S2 is a second screen where the light from P that passes through the slits are absorbed. But in terms of the present hypothesis, a screen can be regarded as a plane of material bodies, atoms, moving in time, each of which might intersect or not with a photon, depending on the distance of each atom from the light source as the photon is deposited, on the spatial orientation of each photon, determining the relative wavelength of the masses, and on the space-time trajectory of each mass in S2 at the moment its wavefront crosses the location of the photon. The light that passes through a slit in the first screen will do so because it is out of phase with all of the trajectories of the masses of the screen, as the latter radiate across the space toward the screen and the deposit of photons by a light source. A few words here on the meanings of frequency and wavelength are in order. Evidently, when a photon is deposited, it has an orientation in space based on the energy of the mass which creates it. When another mass intersects with it, it does so from its own orientation in space, which determines the relative energy absorbed. Here is an alternative representation of the relationship just described between a photon and the second screen with only one slit open. B1 and B2 are two among a myriad of atoms which might intersect with the photon at slit A. The semicircles represent waves along which the spatial trajectories of the two atoms are radiating. They return to the same specific trajectory once per wave cycle. Whether a photon passes the slit in screen S1 or is absorbed by the screen is determined by the moment of emission or deposit, the distance between the source and an atom or the slit in the screen, and the wavelength of the screen relative to the spatial orientation of the photon. The dots indicate the most likely points of intersection of the atoms with the photons. Of course, there are countless atoms that would fill the likely spaces between B1 and B2. Adding another atom between B1 and B2 provides a better idea of how a fuller representation of the interactions would look. without adding a clutter of waves. Because the slit is a little north of the midway point between B1 and B2, the hits at the screen can be expected to cluster there, just as they do in Young's experiment. With another slit opened, A1 has the same attraction as when it was solo, but A2 offers opportunities for interdiction to complicate the pattern on S2. With a second slit, the curious phenomenon first noticed by Young is an appearance of an interference pattern on S2, suggesting that the photons are suddenly behaving like waves. But in terms of the present hypothesis, it is the atoms in screen 2, conceived as radiating toward the stationary photons, that create the pattern. With the portrayal of just two atoms radiating toward the photons, there are already two distinct peaks. If the paths of a cluster of atoms were to be portrayed, there would be a messy but more accurate representation. The wave-like phenomenon can be explained by a coincidence of position of a photon and the atom at its location on its wavefront. The particularities of photons that have avoided absorption in S1 include their orientations in space-time, the coincidence of the moment of their emission with the trajectories of the masses in the screens, all determine a pattern of interception at S2. Adding a third atom between B1 and B2 provides a more fulsome image of how the hits on the screen will take form. The atoms are off-center from the slits, so there is a concentration north of the midpoint between B1 and B2. But what is most significant is the indication of a wave-like pattern forming on S2. If photons don't actually move, and if material bodies radiate approximately in phase, with only minor variations at the subatomic level, their apparent interference can be no more than a pattern, as on a screen, that we identify by analogy with interference found in material media. What is commonly called electromagnetic interference would be described instead as a manifestation of regularities in photon emission that make intersection with masses at consistent distances, moving along particular trajectories, more or less likely. Similarly, light can be considered coherent when photon emission is precisely sequenced and oriented in space to be intercepted by masses along specific trajectories at regular wavelengths. The black dots to the right of S2 represent the number of possible intersections of the three atoms in the screen with a stream of photons. The size of the dots measures how many hits are modeled at each location and indicate a wave-like pattern of crests and troughs, much like an actual interference pattern. But by this hypothesis, no claim of a wave-particle duality of light is necessary to explain such a pattern. They are just clusters of locations where intersections with photons by atoms in S2 seem most likely as they radiate and concentrate across space, determined by harmonics of time, distance, and wavelength. Along with the phenomenon of entanglement, which I'll be discussing next, the double-slit phenomenon may be well suited to the experimental discovery of a more precise nature of four-dimensional, radiant, concentrating, revolving mass. Here is another celebrated phenomenon that defies conventional explanation, what Einstein called spooky action at a distance. Quantum entanglement, as it is called, occurs when pairs of particles are generated in a way that a change to one can be seen to produce an instantaneous change to the other, even at distances that would seem to require an effect transmitted at greater than light speed. It has been reconciled by science only because there seemed to be no alternative. The diagram here illustrates how entanglement can be explained by the hypothesis that light is at absolute rest. There is an entangled photon pair at point P. The photons have been emitted, deposited in space, between two detectors, A and B. Detector A is initially 3 wavelengths from the photon pair. Detector B is 3.5 wavelengths from the pair. The detectors, being massive, having mass, are moving in time perpendicular to space. The emitter and detectors are in line and at rest, so they radiate parallel with each other in time and will intersect the point of emission a half cycle apart. As they move in time, they are understood to occupy the same orientations along their radii each cycle. Hence, each will be at north on the diagram, for example, with constant and consonant frequency. When A intersects with one of the photons at A1 after 3 cycles, B remains 6.5 cycles distant in space from A at B1. The distance from B to the photon pair at that moment is half a wavelength in time. A half cycle later, the dashed lines, B intersects with the second photon at B2, when A is at A2 in space, remaining 6.5 wavelengths from B. Consequently, the detectors indicate that the photons have been evaluated for polarity, for example, when they were seemingly 3 and 3.5 wavelengths from the emission and 6.5 wavelengths from each other, which could be more than twice the distance light would be supposed to travel, although they have not actually moved. Again, granted, this may seem like an odd explanation for entanglement, but it should be favored over the alternative, which is no explanation at all. And I can suggest a means of confirmation. Given the hypothesis, experimentation can be expected to produce an optimum number of confirmed entanglements of photon pairs if the detectors and emitter are precisely in line and one detector is 1/2 wavelength more distant from the emitter than the other, because the more they vary from respective distances of 1/2 wavelength from a photon pair, the less frequent should be the coincidence of their detection of the pair. Experimentation and mathematical formalization are needed to confirm and better define what has been described as the radial trajectory of mass in time across space. But the hypothesis that light is at absolute rest and that the apparent motion of light is just a reflection of an observer's own motion in time has been shown to resolve the wave-particle paradox and to make intelligible the apparent wave-like and non-local behavior of light. Einstein's suggestion in 1905 that light be accepted as both wave-like and particulate, pending a resolution of the conflicting evidence, has become an abiding commitment to paradox, as quantum theory has expanded the range of the counterintuitive to encompass much of theoretical physics. But the fundamental scientific preference for simplicity of description, explanatory power, and logical coherence remains, in principle, as desirable as ever. However much science has accommodated to the supposed strange and paradoxical features of light, a theory that would eliminate the need for such compromise should again be preferred. Nature is not so incomprehensible. Time speeds, light holds fast.